Here we're looking at a question from the rotational motion unit. This is from a 1976 AP Physics exam, so one of the older questions out there, but you see this style of problem repeat itself many times over the years. We have a cylinder, a solid cylinder, that has a cloth tape wrapped around it, and the other end is fastened to a ceiling. I like to think of this problem as like a yo-yo that you're holding the string and you release the yo-yo. So what's it going to do? It's going to fall downward and accelerate downward in a linear sense. That's what we're solving for in question B, that downward acceleration. But also, why this is a rotational motion problem, I would expect the cylinder or yo-yo to be spinning as it falls, and that's because of this cloth tape making it rotate in a clockwise sense. So two goals here. We are looking for a proper force diagram over here on this circle. And then as mentioned, we are looking for that downward acceleration in terms of g, which is a variable for Earth's gravitational field strength. All right, so getting started, we'll look at the force diagram. I think there's a downward force of gravity on this object provided by Earth. We always draw forces of gravity as emanating from the center of mass of the object. So this is a downward force and starting from center. We also have a tension force upward from that cloth tape. This acts at the contact point between tape and cylinder. This is an upward force. And now we're looking at the force lengths or magnitudes. Because of the downward acceleration, I am intentionally drawing gravitational force as a longer vector than the tension force, and that will cause us to accelerate downward. So my forces equation, we need a net force equation, the larger gravitational force minus the smaller tension force. From there, we're thinking about rotation and torque. I need to set an axis of rotation. That's going to be in the middle of the cylinder. That's the center of its rotation. Now, using that point, you can see that the gravitational force acts from that point, and that means gravitational force is not trying to rotate the cylinder. So although this is a force, it is not a torque. Now let's look at tension force. This does not act from the axis. It acts this distance r from the axis, the radius of the cylinder, and this upward force is perpendicular to how we connect the axis to where the force acts from. So it meets the conditions to be a torque, and this is the reason why the pulley will spin clockwise, because tension force provides a clockwise torque. So I'm writing a net torque equation to explain why it's rotating, and that would be equal to the only torque we have, the torque from tension. All right, getting started with the solution for part B, I'm going to isolate this net force equation. Looking at my formula sheet, I'll need the weight equation and my Newton's second law net force equation. I'm plugging those into their respective places, and now I'm just going to rearrange the equation for tension force. I'm going to use that later. From there, starting with my torque equation, some substitutions for that also on my formula sheet. A torque can be set equal to the distance from axis and the force and how perpendicular they are. As well, my net torque equation is I alpha, and so I'm first going to sub those in. On the right, a little more about this variable. R is in there. It is the tension force that provides the torque, and I don't have to worry about this perpendicular symbol because as shown in the picture, the tension force and the R variable are already perpendicular, and there's no trig necessary to find a perpendicular component. Other substitutions, there's a few here. Inertia, that was given in the question as 1/2 mr squared. That's the equation for a uniform solid cylinder. So we're going to punch that right in for I. In place of alpha, I'm not solving for alpha. Remember, I want the downward linear acceleration. That's variable A. So I'm going to use a conversion from my formula sheet to get rid of alpha and then sub in place of that what would be A over R. And now I have the A in there that I can solve for. Tension force, not a variable listed in this question, so I want to get rid of that. This is why I've isolated tension force from the force equation. I'm underlining what tension force is equal to, and that's what I'm going to sub in place of tension force over here. So now looking at this line, there's a few things I can do with algebra to make this look nicer. I see mass m in every term. I'm going to divide that out. I also see r, radius, appearing enough times where I can cancel that out. This r squared divided by r here will take one of the r squareds away, and now I got an r on each side. I can take those away as well. Writing what's left, I'm here. I've got a over 2 equals g minus a. I'm going to add the a from the right side to the left side. So a over 2 plus a would make that 3a over 2. And now the goal is to solve for this acceleration. So I'm going to get A by itself, and I get 2/3 g. So that will be the answer to question B. This cylinder is accelerating downward at a rate that is 2/3 of Earth's gravitational field strength. To summarize this one, I think net torque and angular acceleration is one of the more challenging topics seen in an AP physics class. There are usually many formula sheet connections, as you saw in this problem. We need to be good at force diagrams and considering which forces are and are not torques from it. We need to be good at writing our force and torque equations, here net force and net torque. And we need to be good at algebra. So often tension force will be seen in each equation, forces and torques, and that will be the variable that you use to substitute one equation into the other. If you found this video helpful, then I have other resources that you may be interested in as well. For more information, check out my website, shoot me an email, or follow me on X and Facebook. All of the links can be found in the video description.